Hi everyone, Dr. Mike here. In this video I'm going to talk about a really clinically important topic termed capillary exchange. Simply what we're talking about is that when your heart contracts, so the left-hand side contracts, it pushes blood out of the aorta at a high pressure at about 120 millimeters of mercury, that's the pressure, in that aorta, and then it starts to push its way through to the various branches of the aorta, and as it goes through it ends up hitting around about 93 millimeters of mercury, and as you can see, as it branches through it starts to drop and drop just like a garden hose. You'll find that as you move through the pressure drops until we hit the point of the capillary bed. Now the capillary bed is where all the blood from your heart feeds all the tissues. So we're going to have cells out here that need to be fed, and what they need to be fed is going to be oxygen and nutrients, and there's the nucleus of all these cells. And like I said, oxygen, nutrients come out, and what should happen is metabolic wastes should move back in and excess fluid should move back in, okay? Now what we also have are two ends of the capillary bed. We've got the arterial end and we've got the venous end. And what that means is we've got two parts of a capillary bed we need to discuss and its clinical importance. So as the blood moves through from the left ventricle to the aorta, 120 millimeters of mercury. Then as it branches off, it's around about 93 millimeters of mercury. Then by the time it gets to the capillary bed, the pressure is 30 millimeters of mercury. Now, think about this. As the blood pressure is moving through, it's pushing on the walls of these arteries. That's what blood pressure is, the force of the blood on the walls of the arteries. And it's really strong all through the arteries and arterioles, but there's no holes in these vessels, so nothing leaks out, okay? But by the time we get to the capillary bed, the push on the walls, even though it's only 30 millimeters of mercury, it pushes on the walls and things start to leak out the holes of the capillary bed. Capillaries are porous, meaning multiple holes. Now, as we move through at this arterial end, like I stated, there is the outwards push, the capillary blood pressure, right? The outwards push, and I told you that was 30 millimeters of mercury. Now, what's coming out with this push? Well, fluid is coming out, oxygen's coming out, nutrients are coming out, anything that's small enough to get through these holes. But what isn't small enough to get through these holes? Well, proteins aren't small enough, they can't get through. Cells, like red blood cells and white blood cells, they can't get through, for example. Platelets, they can't get through. So what this means is as the blood moves through, 30 millimeters mercury worth of pressure on the walls, because there's holes, things that small enough can push through, like oxygen, nutrients, they're the main two, ions, like sodium, potassium, magnesium, chloride, calcium, all those, they can all push through. Now, here's the other thing, right? What you'll find is because there is stuff dissolved in the bloodstream and less stuff outside of the bloodstream, there is a osmotic difference, an osmotic pressure difference. What's osmosis? If I were to have a container with a wall in between and fill that container with water, and this wall is permeable only to water, it only lets water back and forth, but doesn't let through anything that I've dissolved in there. And I dissolve a whole bunch of stuff on one side, but not the other. What happens is, all this dissolved stuff on this side has a pull on the water from the opposing side and will pull water towards it. That is osmosis. So when it pulls water towards it, the water level will rise. Now think about this. As the fluid's being pushed out under pressure, capillary pressure, hydrostatic pressure is the term we use, there's stuff left in here, and there's going to be an inward pull as well. And this inward pull at the arterial end is 20 millimeters of mercury, or roundabout. It does vary. So we've got an outwards push of 30, an inwards pull of 20. Where is the net pull or push? Well, we've got a stronger push out. So we have a net push out of 20 millimeters of mercury, which means we have an overall winner here pushing stuff out of the blood vessel. Now, remember, everything's continuing to move through this capillary bed. So that includes the proteins, that includes the red blood cells, white blood cells, and platelets, right? But a lot of the fluid has been pushed out now, right? Which means on the venous end of the capillary bed, you've got a high concentration gradient, but you've got a low pressure. Think about it. If I were to have a garden hose and put a whole bunch of holes down the garden hose and turn it on, the holes closest to the tap are going to have the highest pressure of water squirting out. And by the time you get to the end of that hose, where the holes are present, is going to be less pressure. Same's happening here. 30 millimeters of mercury pushing out, but then all that fluid's coming out. So now you've got, on the venous end, an outward push of only 15 millimeters of mercury worth of pressure. And an inward pull still of around about 20 millimeters of mercury. Now let's have a look. Who's winning on the venous end? The pull in is winning. And again, this is called the osmotic or colloid osmotic pressure. Colloid means protein because the main pulling force here are the proteins in the blood that we term albumin, made by the liver. One of the reasons why if the liver craps itself, we don't have albumin in the capillaries, which means most of the pulling force is not present, which means you get a push out on this end, but no pulling back in on this end, so the fluid stays out here at the tissues, and that's called edema. So when the liver doesn't work, you get edema. Now, as you can see, outward push on this end, inward pull on this end, which means whatever comes out here, we can reclaim on this end. Now, we're pushing out oxygen, nutrients, and ions on this end. What are we pulling back? And fluid, obviously. Let's add fluid here. But what are we pulling back in on this end? We're pulling back in carbon dioxide, right? Because the tissues have used the oxygen, produce carbon dioxide, not nutrients, but waste. We're pulling ions back in, and we're pulling fluid back in, right? And then through the venous system, back to the heart. Now, we don't reclaim everything on the venous end, okay? We only reclaim most of it. That means there's going to be fluid left in this interstitial space around the tissues. What reclaims it? The lymphatic system. And then the lymphatic system will drain it back into the venous system. Now, if we didn't have a lymphatic system, fluid over a single day, enough fluid would build up that we wouldn't have enough blood pressure to keep us alive. So the lymphatic system is important for reclaiming lost fluid from capillary beds. Now, when you have some sort of inflammatory response, let's just say at this tissue, right? It damages the tissues, the cells, they burst, they release chemicals like histamine. What histamine does is it makes the holes at the venous end a lot larger. Now, if these holes are larger, that means now the proteins and the cells can leak out, which now means by the time we get to the venous end, there's no proteins and cells left for that inward pull due to the colloid osmotic pressure or force, and everything again stays out in the tissue. That's why you get swelling at the site of inflammation. So this is capillary exchange.